Imagine, just for a second, that you're peering down into a microscope. You've got a simple drop of water right there on the glass slide. But as you look closer, you notice something kind of crazy. There are these tiny particles suspended in the water, and they are not just floating peacefully. No, they are jerking, dancing, and violently jittering around in total chaos. It literally looks like they're being shoved from all sides by some invisible ghostly force. They just never stop.
Okay, let's dive into this. Because this exact visual anomaly, this bizarre, endless jittering, was an absolutely massive, unsolved mystery for decades. And it isn't just some weird quirk of nature. This is the exact phenomenon that finally, definitively proved that atoms actually exist.
Welcome to The Explainer. I'm so thrilled you're here with us because today we are diving into a true scientific detective story. We're going to see how a seemingly simple observation of flower pollen just floating in a drop of water completely flipped our entire understanding of the universe. We are talking about Brownian motion.
Here's our roadmap for the puzzle we're solving today. We'll start with the dancing pollen mystery, then move into the invisible atomic world. After that, we'll see how Einstein solves the puzzle, followed by Perrin's experimental proof, and finally wrap up with Brownian motion in action.
Starting right off with part 1, the dancing pollen mystery.
To really get this, we've got to travel all the way back to the year 1827. A Scottish botanist named Robert Brown was looking at some Clarkia flower pollen suspended in water under his microscope, and suddenly he sees it. The pollen grains are just locked in this ceaseless, chaotic movement, darting around in these crazy, erratic zigzags. Now, because he was looking at organic material, Brown made a pretty understandable guess at the time. He thought, hey, maybe this pollen is actually alive. He really thought this movement was just a built-in feature of biological life.
But Brown was a top-tier scientist, right? He wanted to be absolutely sure. So he brilliantly sets out to debunk his own life theory. He decides to test completely dead inorganic stuff. We're talking ground-up glass, dust, ash, little flakes of minerals. And when he puts those non-living things in water under the microscope, well, they danced too. They jittered around with that exact same chaotic energy. So this creates a massive intellectual void for scientists. Because if these particles aren't alive, what in the world is actually moving them?
Which brings us to part 2, the invisible atomic world.
Now we get to our prime suspects. Atoms and molecules. You have to remember, back in the 19th century, the idea of atoms was actually super controversial. A lot of scientists thought they were just a convenient mathematical trick, not, real physical things. But to solve our mystery, we have to understand what we now call Brownian motion, named after our botanist friend, of course. It's defined as the continuous, chaotic, and random movement of microscopic particles suspended in a fluid or a gas.
Now, what's really interesting here is the wild contrast between how we see things and what's actually happening. In our macro world, just everyday life, a glass of water sitting on your kitchen table looks perfectly still and calm, right? But if we zoom way down into the micro world, that exact same water is a chaotic, non-stop storm of hyperactive molecules constantly smashing into each other.
But here was the massive roadblock that totally stumped 19th century scientists. Even if they believed in water molecules, how could those molecules possibly move a giant piece of pollen? Think about it. To a single water molecule, a pollen grain is roughly the size of a planet. Critics argued there's no way something so minuscule could physically push that massive grain. And even if they did hit it, there would be millions of collisions happening from all sides at the exact same time, so the forces should just cancel out and leave the pollen sitting perfectly still.
Moving on to part 3, Einstein solves the puzzle.
So, this mystery just hangs around for nearly 80 years. That is, until the master detective himself enters the scene, a young Albert Einstein during his famous miracle year. It took almost a century from Brown's first observation in 1827 to get to Einstein's math in 1905, which then laid down the exact path for actual experimental proof just a few years later in 1909. And this brilliantly illustrates Einstein's genius. He didn't even use a microscope. He used pure math. By deriving equations for the mean squared displacement of these particles, he took a statistical approach. He basically proved that yes, millions of water molecules are hitting the pollen from all sides, but the collisions are totally random.
Because of statistical fluctuations, at any given fraction of a microsecond, you might get slightly more molecules slamming into the left side of the pollen than the right side, and that tiny split-second imbalance is exactly what shuffles the pollen grain and causes that crazy zigzagging. Let's break down the mechanics of this chaos without getting bogged down in the math. First, water molecules are moving incredibly fast, just completely driven by thermal energy, or heat. Second, they are constantly swarming and bombarding larger suspended particles, like our pollen. And third, those uneven, statistically unbalanced strikes cause those random jerks. Einstein gave us the exact formula to predict how far and fast a particle would drift based on the fluid's temperature and thickness. It was a total game changer.
Which leads perfectly into part 4, Perrin's experimental proof.
Now, Einstein's math was beautiful, but science demands physical proof. So following that 1905 paper, the brilliant French physicist Jean Perrin took Einstein's equations straight into the lab. He meticulously recreated the exact conditions to test the math, spending hours tracking the movements of tiny resin particles in water. And guess what? The particles moved exactly, and I mean exactly, how Einstein's formulas predicted. This was the ultimate, undeniable confirmation that the atom was a physical reality. It was so huge that Perrin actually won the Nobel Prize in Physics for it in 1926.
What's even more mind-blowing is that by tracking this chaotic displacement, Perrin was actually able to compute Avogadro's number. That's the unfathomably huge number that dictates the scale of atoms and molecules. He literally used the visible jitters of a particle to accurately estimate the physical sizes of the invisible molecules hitting it. I mean, what an absolute triumph of human intellect.
Let's move to part 5 and see how this builds into Brownian motion and action.
So why does this matter today? Well, Brownian motion isn't just some dusty history lesson. Understanding this chaotic microscopic dance is the absolute foundation for cutting-edge tech. We're talking statistical physics and chemistry. Without this, we couldn't develop modern nanotechnology, because any machine you build at the atomic level is constantly fighting this random, violent thermal motion. In medicine, this helps us understand how particles diffuse, which is absolutely crucial for targeted drug delivery systems inside the human body.
I really love this thought from the biophysics world. It is simply amazing that cells can do anything when their underlying motion is random. Think about that. All the beautifully organized complexity of biology, your beating heart, your firing neurons, your DNA, it all somehow survives and thrives in an environment that is fundamentally chaotic and violently jittery.
So, the crucial point is this. By simply looking through a lens and watching a tiny, seemingly insignificant piece of pollen twitch in the water, humanity was finally able to see the invisible atomic world. It proved once and for all that the universe of matter isn't static. It is made of endlessly moving, frantically colliding particles.
The next time you look at a still glass of water, remember the violent, beautiful physics operating just beneath the surface. Because even in a simple, quiet drop of water, an entire chaotic universe is hiding.
I really hope you enjoyed this journey into the microscopic world. Want to understand how other tiny phenomena have completely revolutionized modern science? Make sure you subscribe to the Code of the Universe channel. This is the place where the complex becomes simple. Thanks so much for joining this explainer, and we'll see you next time.